So what I want to do here is that now we have to then effectively talk about part 5, 6, 7, and 8 in order to talk about the lab. And I don't really want to talk too much because I think the first part of the lab really sets you up to do the rest of the thing. So now I'm going to go in and I'm going to change my share to right here. So now let's go look at these things. So the next part that we're looking at is we're looking at part 5. And in part 5, you're looking at a cost of energy. Now that you've done the bike on part 4, you'll be able to really get a good sense of what do they mean, what it means to do work in order to create some type of watts of power. Now, if you look at the definition of power, what you're finding here is that power is equal to energy divided by time. If you now solve for energy, this is then going to be power times time. So then if you look at your PG&E bill, what you're finding here is that the way they're measuring this thing is that, look at your PG&E, it reads kilowatt hour. In other words, it's kilowatts times hour. This is a unit of energy or work. And you could see here is that when you look at power, they're talking about kilowatts. And when they're talking about time, they're talking about an hour. So they're charging you for how much work. So now that you have a little bit of sense of what this is here, then go in and look at what you're looking at here and answer the questions. How much do how many people would have to pedal in order to put out 1,000 watts? And then just go and answer the questions. But that's reference to that. So now let's go to part 6. In part 6, we want to look at the forms of energy. And conversion. Now, when I think about energy, energy is energy. What a brilliant statement, huh? But energy is just energy. And the way I think about this here is that I think about soup. If you make a soup and you start to add all these ingredients, you might be able to pick out a little bit of this or a little bit of that, but a lot of the times, all those meld together so well, assuming that you make good soup, that is, and it really acts as one. So you could imagine that you have a pot here, and if you have this pot of soup that you have now created here, once you have this pot of soup, I could then effectively pull out of this energy soup and transform it into other types of things. So what I mean by that is that from the work energy theorem, what we've been talking about here is we say here is that work does not disappear. But reappears as energy. In the language of total energy, instead of the work not disappearing, is we say that the total energy does not disappear, but reappears as other forms of energy. So when you're looking at this hydrogen fuel cell, or the falling weight to light up a light bulb, or whatever it is that you're going to be looking at here, what you're going to find here is that energy can convert. And as it converts, and one form that we have the example here is that we have a roller coaster cart, going down / up, the ride. What you're finding here is that you have multiple possible conversions of energy into other forms. And so when you're looking at the hydrogen cell, fuel cell, you're going to see that you can go from step to step to actually trying to understand what that is. And we listed the energies last time, but you could imagine that this is just a big melting pot of energy, and somehow you're converting all of these here. Then we go to part 7. If you go to part 7, what we're looking at here is that we're going to be looking at kinetic energy, and speed. Now, effectively, this is a really famous experiment early on. And I'm sure that if you could nail Paul down for a little bit, sometime outside of lab, or maybe even during the lab, after you're done with the experiment, there was this question about what does it mean when you are converting potential energy into kinetic energy. So, in other words, you could imagine the following situation. So imagine that you have a ball that you're going to drop into mud. Okay, so here's this ball that you're going to drop into mud. And now what you could imagine here is that you start off at a lower height, and you get to you go and you're getting to higher and higher and higher. What would you expect the ball to stick into the mud? If it falls from a higher height, you would expect that it's going to go further into the mud. If it falls from a lower height, you would expect that it's not going to go as far into the mud. So in essence, what you're finding here is that you are converting, in this case, gravitational potential energy into kinetic energy. And then by looking at this thing, you're essentially asking, what is this quantity that why does it go further into the mud as I go higher and higher? And you'll see here is that as you read through this thing, you're going to start to actually look at this thing, what actually happens. And the same thing happens here, but what you're going to be doing here is that you're going to be using a launcher. Instead of dropping it into mud, you could imagine that you're going to have a gun that you're going to be shooting. And I have a ball here, is that now you have a spring that you're compressing. So as you compress this spring, you could imagine that if I compress it more, it's going to go higher up. If I compress it less, it's going to go not so high up. And so somehow what you're trying to do here is that as you're looking at these heights and they're getting higher and higher and higher and higher, the question is, what's the relationship between the height and the compression, or the height and the speed? But you'll have to ask Paul, is this Paul, was the name of the woman what was her name?
Châtelet, I think you're talking about.
Which one?
Emily du Châtelet?
Yes, that's the woman. Yeah, Paul's an expert at this, so he'll be able to tell you more about that than I could. And then finally, there's part 8. And in 8, you're essentially talking about the efficiency of energy conversion. And so this is actually a story made up by John and how you're transferring energy. And the one thing that you want to think about, that as you're transferring energy, you got to remember about the heights. Okay. I think this one's pretty self-explanatory, but what I would do here is that I would try to look at the energy bar diagram flow. By the way, in the lab, it says 7. It should have said 6, not 7.